Hello, my name is Neil Sikka. I'm the founder of A1LOGIC, and I'm here to present to you today how we used the Zen hypervisor to implement hypervisor-enforced data loss prevention. So an outline of what I'm going to talk about. First, I'll talk about what the problem was that we are trying to solve and the goals in our implementation's design, followed by a technical overview of the different subsystems in the implementation. So the problem, in short, is data breaches. You see them all the time in the news. You see massive amounts of customer and organization data leaked by malicious insiders or attackers or by accident. And the real problem is that, if you look at it from a technical point of view, the real problem is that the raw bytes of data are available to, at a programmatic method, to applications and to users, if they're technical users. There's many ways to exfiltrate data from an organization by, for example, using zero-day exploits, using kernel mode rootkits. You could even have a technical user with a kernel debugger stealing memory out of a process's data. Stealing data out of a process's memory. So there's many ways to steal data, including lost devices. And just like the antivirus industry has gone, where detection doesn't work anymore, the same is true for the DLP, or data loss prevention industry. Detection is dead. I'll give you an example here. If you look at the top right, you see 999-961-770. Suppose that's a social security number that somebody has inside of an organization and they want to exfiltrate it. If you're trying to detect things, there's literally an infinite number of ways to encode that same social security number. I've given you two examples up here. The greatest THR 33-digit integer. To you and I, it's obvious that it means 3, but to a machine, it's not so obvious. So you say the greatest 3-digit integer, 999, number of C3NTS in $-4, 96. The year the US Declaration of Independence was signed, minus a picture. So that's another example of one of the infinite number of ways that you can encode the same data to exfiltrate out of an organization. If you're trying to do heuristics, like all other DLP solutions are today, both of these can be fabricated and used against you to exfiltrate data. There's even some that use OCR, that's considered advanced, but then you have a picture which is 6, which is not even clear. It's granular and it has dots on it, so it's very difficult for a machine to tell. Another example of exfiltrating the same data is I can see 999 green ducks sitting in a row. 96 of them have extra long beaks. There are 1,770 ducks total in the flock of ducks. Now, am I talking about what I did this weekend, or am I talking about a social security number I'm trying to exfiltrate? You can algorithmically generate the strings here and exfiltrate social security numbers. It's not that hard. So the problem is that, in general, the overall problem is that DLP is heuristic today, whereas an algorithmic approach is needed. So the goals for our design were multiple. First of all, we want to protect data under the assumption of compromised users, devices, and networks. So that means that Edward Snowden is inside of your network right now with a kernel debugger or a USB drive trying to steal things. All of your devices have kernel mode malware, for example, and your traffic is being sniffed by outsiders. If you look at some of the recent revelations, it was found that people are actually attacking routers and switches and trying to exfiltrate data from an organization. Second goal is that we want it to be algorithmic rather than heuristic. We want it to be transparent to legacy applications and to users, because both of them should not know that this implementation will be running underneath them. Users don't want to learn stuff, and legacy applications cannot change or be made aware of what we're doing here. This allows us to be agnostic to both the user experience and to the legacy applications. Finally, we want to use high-strength approaches, such as hardware enforcement for the segregation of data, and high-strength cryptography. So the solution is hypervisor-enforced data loss prevention. It's a look but don't touch scenario in that the user can see the graphical output of the parsed bytes in memory, but cannot touch the bytes themselves. And they can modify the parsed output, but they cannot, again, touch the bytes. Basically, we have a container, a virtual machine container, in which we run an application. And any data inside of that application that the application operates on obviously has to be unencrypted for it to be unmodified, for the application to be unmodified. And we encrypt data before it is written out of the virtual machine container. And we decrypt it after it's read into the virtual machine container. Additionally, what we're doing is able to lock down data per user, per device. And I will go into that in more detail. And we aim to be a software-only solution. OK, so here it is. Here's the architecture of what we're doing and our virtual machine layout. As you can see on the bottom, you have all the hardware devices there. You have a type 1 hypervisor, such as Zen, running on top of that. And you have many virtual machines or domains. Domain 0, you have trusted and untrusted domains in the middle there. And you have a display domain, which is similar to OpenXT's UI VM. And you have a data store on the top left, which is basically accessible to both the trusted and untrusted domain. So the untrusted domain is online, so it has network connection. The trusted domain 1, we'll use 1 in this example, trusted domain 1. Trusted domain 1 is offline. So what happens is the user is using the untrusted domain, maybe a browser, and downloads a file. So this file would be saved onto the data store. But the trick here is that the file is encrypted with a key that is not accessible to the untrusted domain. So the user and any malware in the associated domain cannot unencrypt the data. The trusted domain, however, both of the trusted domains have the necessary keys required to decrypt the data. So when the user double-clicks on the file in the untrusted domain's data store, the data store, there's a message sent from the untrusted domain to the trusted domain to please open this file, at which point the data store is read by the trusted domain, and the file is decrypted in memory, and it is executed upon by the associated application. And all the while, throughout this whole process, any graphical output from any of the domains is forwarded to the display domain. This is similar to seamless mode in VirtualBox, or there's other implementations of similar things. And we have VTPMs connected to the trusted domains. And these VTPMs can protect sensitive data and can only unlock them for the trusted domains. So the environment in which we built this implementation was Windows 7 64-bit untrusted domain, trusted domain, and Zen 4.4.0, and paravirtual drivers in the untrusted and trusted domain, and 64-bit Linux kernel 3.19.1 running in DOM0. So the first subsystem is the messaging subsystem. Because the trusted domain is offline and the network stack is a very big attack surface, as has been seen multiple times in the near past in the security industry, we have the trusted domain offline, and all the communications go through Zen Store. We also pass configuration and small messages through Zen Store. Large amounts of data are passed through grant pages and event channels, such as with many of the drivers that are available for Zen. We have two protocols that we implement over the messaging subsystem. One is the seamless protocol, and one is the shunt protocol, which I will cover both of in more detail. So the graphics subsystem, as I mentioned, is similar to VirtualBox's seamless mode. And we have a protocol with two endpoints. One endpoint would be the QEMU model of the trusted domain. The other endpoint would be the user mode, an application we call seamless.exe in the display domain. The trusted domain hooks window information. In this case, we're using user32's setWinEvent hook API to get window coordinates. We take those window coordinates and we write those coordinates to an I/O port, obviously through a driver, to I/O ports exposed by by QEMU's virtual graphics implementation. Then those coordinates are taken and sent over the seamless protocol to the seamless.exe in the display domain. And we have implemented this using an XPDM display driver architecture. We made heavy modifications to the QEMU SDL layer. That's where a lot of the libraries and the hooks are implemented. What we did was we hooked the mouse and keyboard APIs in the SDL layer of QEMU, which emulates the trusted domain. And we are reading input from the display domain's seamless.exe for the mouse and keyboard events. And every time something happens, there's an event channel that's fired, which would be the protocol event channel for the mouse and keyboard events. Similarly, we have the exact opposite but flipped. We have to share the graphical output from the trusted domain. So what we do is we allocate grant pages, and we use those grant pages as the display surface. So in QEMU, you have a display surface that is rendered to, you can say, from, that's where the scan lines are drawn. So we do that on a large amount of grant pages. And we fire an event every time the rendering is completed. And we have, as I mentioned, a seamless.exe application running in the display domain. And it captures the keyboard and mouse events from the seamless.exe application, and it passes it to the backend, which is the SDL layer of the QEMU of the trusted domain. And also the windows, we clip images of the display surface at the coordinates specified by what we captured in the trusted domain. Now, we had a similar problem to what OpenXT had. I think in a previous talk they were talking about it. How do you share many grant references? In this case, you have a 3 megabyte display surface, and you want to share 3 megabytes worth of grant references. How do you do that? XenStore only supports strings, and trying to write that many numbers would not work. So we wrote some custom grammars, LALR grammars, to parse the grant references and then generate smaller strings that we can store into XenStore, and then do the opposite on the receiving side. So here's the last 2 slides explained in a graphical format. So you can see we have a display domain, which runs a seamless.exe application, and we have multiple domains, trusted and untrusted, that provide input and take output from the seamless.exe application. So let's take this trusted domain example. You see that there's a keyboard and mouse event channel every time there is some data ready on the seamless protocol grant pages from the display domain, and that's the pages that contain the user's keyboard and mouse information. And we have we have another event channel for every time the display domain is ready to read, or should be notified to read from the display surface. So every time the rendering is completed, SDL sets the event channel, and the display domain now has a surface that it can read. And this is symmetrical for the untrusted domain. So you can probably get the sense that now in the display domain we have an amalgamation of the windows from multiple other virtual machines. Now I'm going to cover the storage subsystem. This is the data store that you saw that is shared between the trusted and untrusted domain. So we needed to share data and files, possibly big files, back and forth, but we don't. The conventional way of doing that is using SMB or some network protocol, but the problem is that we don't have, and we don't want to have, any network stack in the trusted domain. So what we did is we were looking around for file systems that we could use. There's Oracle's OCFS for Windows, but that requires many complex configurations, and IBM's GPFS, but we did not want to live with those limitations. So instead, we had a virtual disk formatted with NTFS that we shunt back and forth between the trusted and untrusted domains. The shunt disk is mutually exclusively mounted to either the trusted domain or the untrusted domain, and it's always mounted to one of the two. And we wrote a file system mini filter that will automatically encrypt any writes coming out of the trusted domain and automatically decrypt any reads coming into the trusted domain. And then we also built a shunt protocol for communicating messages back and forth between the trusted and untrusted domains. And that shunt protocol, this, is one of the ones that we have implemented over XenStore. So there's three basic commands. One is open, where a user double clicks on a file, and the untrusted domain tells the trusted domain, hey, please open this file. Once the shunt has been shunted over to the trusted domain. There is the detach command, which is initiated from inside the DOM-U, that basically tells DOM0 that, okay, we have unmounted and gracefully unmounted the virtual disk, and now please rip it out using an Excel block detach-like API. Then there is the application exit, which basically says from the trusted domain that the application that is executing on this sensitive data has quit, and now we can shunt the shunt disk back to the untrusted domain. And the endpoints of this protocol are one in the trusted domain, one in the untrusted domain. And here is a diagram of that. So you can see the trusted domain and untrusted domain share a virtual disk that is managed by domain 0. And the XenStore database is also managed by domain 0. And that is the communication medium over which the trusted and untrusted domains communicate. All of their communications, in this case, though, we're talking about the shunt protocol. Now, for the crypto subsystem, we are using a PGP-like design in which you have a DLP key, which is asymmetric, and which encrypts a file key, which is symmetric, which encrypts a file. These DLP keys are protected, and they are locked down per user per device, and they're protected by the VTPMs, as I mentioned before. You can have multiple DLP keys per device and multiple DLP keys per user, but one DLP key per device per user. So for example, if Alice wants to send a file to Bob, Alice could send it to Bob's desktop, not his laptop. And only Bob can open it only on his desktop. Now, if Eve comes to Bob's desktop and tries to open it, she won't be able to open it. So it's only Bob on only his desktop. So in this way, we're locking down data per user per device. And the file key that I mentioned is the one that is handed over to the mini filter driver for any encryptions or decryption operations. Yeah. Yeah.
How does so PGP, you've got a lot of key sharing.
Yeah, yeah.
Do you guys have a solution do you just use actual PGP to do like a normal key server or something like that?
Yeah, I mean, so we're not presenting this is a hypervisor assignment, so we want to focus on the hypervisor piece. But we are sharing keys across an organization using public and private, asymmetric keys, and yeah, it's standard. Nothing, there's no innovation there per se. There is the innovation, this is the innovation. Yeah.
Thanks.
So as far as the security architecture goes, we consider the following domains sensitive. Anything that contains unencrypted data, unencrypted keys, or parsed output from sensitive data. So that implies that it would be the trust domain, the display domain, and domain 0, which is the control domain over the whole hypervisor. Trusted domain is based on known good hashes. So if there is some, basically we're able to check the state of the trusted domain to make sure that it is trustworthy and can be and should be booted and trusted with sensitive data. Finally, similar to OpenXT's VPN VM, where they have a VM in between a full operating system and a device model, we have something similar in that we have an encryption VM where we can encrypt encrypt data with a separate key that's not accessible to the trusted domain in case there's some sort of exploit through malformed data in the trusted domain. And it's also not accessible to domain 0. So that's all I had today. Thank you for your attention. Any questions?
Do you have a demo?
Oh, you asked that earlier. So yeah, we had 25 minutes. So but actually, if you want to, you have my information. We can set up something.
Okay, cool.
Mm-hmm.
You talk about the virtual disk that's shunted between a trusted domain and an untrusted domain. At a time, it can be associated only with one domain or another domain.
Yeah, it's mutually exclusive.
It's mutually exclusive. So doesn't it necessitate some kind of synchronization
Yeah.
to access that disk? Or is that problem addressed?
Yeah, that's the protocol. That's the shunt protocol.
Okay.
So basically, trusted domain would say, I'm ready for it to be ripped out. And then that gets passed to domain 0, which does the ripping out. And automatically, because domain 0 knows that it has to be in one of the two VMs, and it's not in this one. Therefore, it must be this one. So automatically shunts it back and forth.
That's the problem. Both of the VMs wants to access that disk. Then, that
So yeah, we have a state machine implemented to model this protocol. So that's not a valid state to be in. You should never get to that state.
And one more question just came to my mind. Once we have the encryption done, whether it is trusted domain, and once we have that file we talked about, the infected file or the wrong file, in the memory, then there is no way to protect that file from exploiting scenario. The file is loaded, it has been encrypted, but after that, what happens? It still is infected.
So you're saying the file that is open in the trusted domain is infected?
No. It was downloaded in the untrusted domain by the network, and it's opened by untrusted domain, so it will be in the process of untrusted domain. Yeah, that's fine.
No, it's not opened by the untrusted domain because it doesn't have the key. Only the trusted domains have the key to open a file if it's
But if
encrypted.
It wants to open that file, it will send a message to the trusted domain, and then trusted domain will take it and then open the file.
Yeah,
That's
yeah.
right.
So
Open the process address space of the untrusted domain, not the trusted domain, right?
the exact opposite. It's open in the address space of the trusted domain, not the untrusted domain, because the sensitive information is open only in the trusted domain because only those virtual machines have the keys available to decrypt.
Right. If it's open in the process address space of the trusted domain, then and if the file is infected, then how you're going to prevent trusted domain from getting exploited by that file?
Yeah, it could get exploited, but then we rely on known good hashes
Okay.
of the trusted domain.